You think concrete is dead. It's the most ordinary material in your world. Sidewalks, bridges, parking garages, apartment blocks, you pour it, it hardens, it reaches its design strength in a matter of weeks, and then it simply exists, static, inert, finished. But that assumption is wrong. Some concrete is not finished. Some concrete is still changing, still strengthening, after 2,000 years. That sounds like exaggeration. It sounds like myth wrapped in archaeology. But walk through ancient Roman harbors, run your hand along submerged breakwaters, and you touch something unsettling, structures that have endured relentless waves, saltwater corrosion, and tectonic stress for millennia. Modern marine concrete often struggles to survive a century without serious degradation. You think technological progress moves in a straight line. Newer must mean stronger. But here, the timeline bends. Roman concrete does not merely survive. In some environments, it appears to improve over time. Microstructures within it continue to evolve long after the initial setting. Chemical reactions persist. Crystals grow. Bonds tighten. You think hardening is an event. Pour, wait, cure, complete. But in certain formulations, hardening is a process that refuses to end. This destabilizes more than engineering. It challenges how you imagine materials themselves. We treat solids as static. Once something becomes stone-like, we assume its internal story has stopped. But matter does not freeze simply because it feels rigid to your touch. At the microscopic level, atoms continue to rearrange. Fluids move through pores. Reactions advance at glacial speeds. What feels permanent may still be in motion. The Roman formula relied on volcanic ash specifically, ash rich in reactive minerals, combined with lime and seawater. The result was not just a quick-setting binder, but a chemically dynamic composite. Over decades and centuries, interactions between seawater and the ash created new mineral phases inside the concrete. Tiny crystalline structures formed within cracks, reinforcing weak points. You think cracks mean failure, but in this material, cracks became opportunities. Instead of accelerating decay, seawater triggered further strengthening. The ocean did not simply attack the structure, it participated in its evolution. This reverses a common intuition. We assume exposure degrades. Here, exposure sustained. The deeper discomfort lies in time. Modern infrastructure is designed with projected lifespans 50 years, maybe 100. Maintenance cycles are planned accordingly. But imagine designing something that continues to mature across generations, a structure that grows more resilient as centuries pass. Concrete is supposed to be mundane, yet buried within ancient harbors is a lesson about chemistry unfolding across timescales that dwarf human planning. You think materials are static once solidified, but some materials are still becoming what they will be. And if concrete can continue hardening for 2,000 years, the real question is not just how, it is what we misunderstood about the nature of solidity itself. When you hear that concrete is still hardening after 2,000 years, your first instinct is to translate it into something familiar. You imagine a slow continuation of the same process that happens in the first few days after pouring. Cement reacts with water, crystals form, the mixture stiffens, strength increases. Extend that timeline, and perhaps it simply keeps going. But that picture is incomplete. You think hardening is the same as drying. It isn't. Concrete does not harden because water evaporates. It hardens because of chemical reactions between water and compounds inside cement. This process is called hydration, and it transforms a fluid slurry into a rigid network of interlocking minerals. In modern concrete, most of this reaction occurs within the first month. After that, strength gains slow dramatically. That is why the idea of 2,000-year hardening sounds implausible. Modern concrete reaches most of its structural capacity quickly. What remains is gradual aging, not dramatic transformation. So what made ancient concrete different? The key lies in composition. Modern concrete relies heavily on Portland cement, a finely ground material rich in calcium silicates. When mixed with water, these compounds form calcium silicate hydrate structures that bind aggregate together. It is efficient, predictable, and fast. But it also creates vulnerabilities, especially in marine environments where chloride ions penetrate and corrode reinforcing steel. Roman concrete did not use Portland cement. It used lime and volcanic ash, particularly ash-rich in aluminosilicate minerals. This ash, known as pozzolana, reacted with lime in the presence of water to form a different set of binding phases. The chemistry was slower, less uniform, but deeply resilient. You think faster is better. In construction timelines, it usually is. But chemically, speed can mean brittleness. When seawater infiltrates modern concrete, it often accelerates deterioration. It leaches calcium, expands cracks, corrodes embedded metal. The environment becomes an enemy in Roman marine concrete. Seawater did something unexpected. Instead of merely eroding the material, it reacted with unhydrated lime and volcanic components to form new minerals, particularly crystalline structures like aluminum tobermory. These crystals grew within pores and cracks, effectively stitching weaknesses over time. Hardening in this context was not a single phase. It was iterative. You think a crack marks the beginning of decay, but in this system, cracks could become sites of regeneration. This difference forces you to reconsider what finished means for a material. In modern engineering, we aim for controlled, predictable reactions that complete within days or weeks. The product is stable, but chemically quiet. Roman concrete remained chemically active for centuries. The ash particles did not fully react during initial mixing. They remained as latent ingredients, waiting for water and time to activate them. The ocean provided both. Slowly, across decades and centuries, additional mineral phases formed, reinforcing the matrix from within. What appears miraculous is actually geological in pace. You think materials operate on human timescales, but geology teaches otherwise. Rocks transform over millions of years under pressure and heat. Here, something similar happened at a smaller scale, a human-made stone participating in long-term mineral evolution. This is not magic durability. It is chemistry extended across time, and it suggests something unsettling. Perhaps our modern obsession with immediate performance overlooked a deeper dimension of strength, the ability to evolve rather than merely resist. If that is true, then the lesson of ancient concrete is not nostalgia. It is a challenge to how we define solidity itself. To understand why Roman concrete could continue hardening across centuries, you have to stop thinking of it as a construction material and start thinking of it as a controlled geological experiment. You think stone is something nature makes slowly, under pressure and heat, deep inside earth. Concrete is something humans make quickly on construction sites in rotating drums. The two seem fundamentally different, but chemically they are closer than they appear. Roman engineers unknowingly created a low-temperature rock-forming system. When they mixed lime with volcanic ash and seawater, they set up a reaction environment rich in calcium, aluminum, silicon, and water exactly, the ingredients required for mineral growth. What they poured into wooden forms was not merely wet cement. It was a mineral nursery. In modern Portland cement, the hydration process is relatively controlled and front-loaded. Calcium silicates react rapidly with water, forming a dense binding phase. Most of the reactive material is consumed early. The system stabilizes. What remains is largely inert filler and locked in microstructure. Roman concrete was less chemically complete at the start. The volcanic ash they used contained glassy particles and crystalline fragments formed during explosive eruptions. These particles were reactive, but not instantly so. Many remained only partially engaged during initial curing. They sat inside the matrix like dormant seeds. You think a finished structure should be chemically quiet, but this structure was chemically patient. When seawater penetrated the material, it carried dissolved ions that interacted with those dormant ash particles. Over time, this interaction produced rare minerals, most notably aluminum, substituted tobermorite and phillipsite. These are not typical products of modern cement chemistry. They are minerals more commonly associated with hydrothermal geological environments. Their presence matters. Tobermorite crystals are strong, plate-like structures that interlock within the concrete's microscopic pores. As they grow, they reinforce the matrix from within. Instead of cracks widening unchecked, new mineral growth can bridge and strengthen weak regions. You think durability means resisting change. Here, durability emerged from ongoing change. The system did not aim for perfect initial density. It allowed porosity. It allowed seawater in. That seems counterintuitive from a modern engineering perspective, where impermeability is often treated as a goal. But permeability enabled reaction. Seawater was not merely tolerated, it became a reagent. Magnesium and other ions contributed to the formation of additional mineral phases that gradually altered the microstructure. Over decades, the material's internal landscape shifted, voids partially filled, bonds reorganized, crystals extended. This was not rapid strengthening. It was incremental consolidation. If you could zoom into a Roman harbor block over 2,000 years, you would not see a static cross-section. You would see a slow choreography of dissolution and precipitation, of minerals forming where stress or cracks created opportunity. It behaved less like a poured slab and more like sedimentary rock adjusting to its environment. There is another layer to this story. Modern Portland cement production requires high temperatures, around 1,450 degrees Celsius, to form its reactive compounds. Roman lime production used lower firing temperatures. The resulting material contained more unreacted lime clasts, small fragments embedded in the matrix. For years, these lime clasts were considered flaws, white chunks interrupting uniformity. Recent analysis suggests otherwise. When cracks formed and water entered, those lime clasts could dissolve partially and re-precipitate calcium carbonate, effectively sealing microfractures. What appeared to be imperfection was a reserve of reactive material. You think uniformity equals strength, but controlled heterogeneity can provide resilience. Roman concrete was not optimized for rapid strength gain. It was optimized, perhaps unintentionally, for long-term mineral evolution. This shifts the philosophical lens. We design materials to reach peak performance quickly. Our infrastructure is evaluated on early compressive strength, cost efficiency, and predictability. But ancient concrete invites a different question. What if the highest form of strength is not static resistance, but adaptive transformation? A material that continues to reorganize internally in response to its environment blurs the boundary between engineered object and geological process. It is still stone, but it is stone that remains in conversation with water, time, and chemistry. And that conversation has lasted 2 millennia. If Roman concrete behaves like geology, then the Roman Empire did something subtle without knowing it. They recruited time itself as an engineer. You think engineering is about control, precision ratios, exact measurements, predictable outcomes. Modern construction reflects that philosophy. We calculate load distributions, curing times, tensile strengths. We design for certainty within known limits. But Roman concrete suggests another model. It suggests that engineering can extend beyond the moment of construction. When a modern structure is completed, its chemical evolution is largely finished. Its future is primarily mechanical, expansion and contraction with temperature. Stress under load, gradual fatigue. Chemically, it is quiet. Aging often means deterioration in Roman marine concrete. Aging meant participation. The environment did not simply impose wear, it contributed to growth. Seawater carried dissolved elements into the structure. Microscopic channels allowed those elements to interact with unreacted volcanic ash and lime clasts. New crystalline phases formed sometimes decades after the original pour. You think stability means isolation from environment, but here stability emerged through interaction. The Mediterranean became part of the building process. This has implications far beyond ancient harbors. Consider how we design coastal infrastructure today. We treat salt water as corrosive, aggressive, something to keep out at all costs. Steel reinforcement must be protected from chloride attack. Concrete mixes are modified to reduce permeability. We fight the ocean chemically and structurally. The Romans did not embed steel in their marine concrete. They did not depend on metal tensile reinforcement that could corrode. Their material strategy was different from the foundation up. It relied on mass, chemistry, and mineral evolution rather than on internal steel skeletons. You think technological progress always means adding complexity. Sometimes it means understanding constraints differently. Modern researchers studying ancient Roman samples have identified mineral assemblages that continue to develop long after initial curing. These minerals form in low temperature conditions, but resemble those created in hydrothermal systems deep underground. It is as if parts of the harbor blocks became miniature, self-contained geological environments. The longer they sat in seawater, the more certain mineral phases accumulated. This reframes durability. In modern systems, durability often means resistance to change. Minimize reactions, minimize intrusion. Maintain original structure as long as possible. Roman durability came from selective change. The matrix was not locked permanently in its first configuration. It retained chemical potential. The slow formation of additional binding phases reduced porosity and reinforced weak zones. Time did not simply pass over the material. Time modified it. And this points toward a larger tension in modern engineering culture. We prioritize speed. Construction schedules are compressed. Materials are optimized for rapid curing and early strength. Financial and logistical pressures reward immediacy. Long-term mineral evolution is rarely part of the design conversation. You think progress moves toward faster solutions, but sometimes speed narrows imagination. Ancient concrete was slower to reach full potential, but its potential extended far beyond the initial build phase. It integrated environmental chemistry into its structural life cycle. This does not mean Roman methods were universally superior. Their concrete was not suitable for all structural forms. It lacked the tensile strength that steel reinforcement provides. It was massive, not slender. It enabled domes and harbor walls, not high-rise glass towers. But it demonstrates an alternative engineering philosophy, designed not just for the moment of completion, but for centuries of chemical dialogue. In that sense, Roman concrete was not frozen in time. It was built for time. And perhaps that is why it still stands, because its creators, intentionally or not, left room for the future. When you first hear that Roman concrete is still hardening after 2,000 years, it sounds like a historical curiosity, an impressive detail, a clever ancient trick, but by now the story feels different. You think strength is a fixed property, a number on a test, a compressive value measured at 28 days, a certification stamped into a material data sheet. But Roman concrete suggests that strength can be a process. It was not strongest the day it was poured. It was not chemically complete when workers removed wooden forms. Its internal story continued long after the empire that built it dissolved. That forces a deeper question. What do we mean when we call something solid? We use solidity as a metaphor for certainty, for permanence, for reliability, a solid argument, a solid foundation, a solid plan. The word implies immobility, yet this ancient material shows that what appears immobile can still be evolving at the smallest scales. Crystals continue to grow. Ions continue to migrate. Microstructures continue to rearrange. Change does not always weaken. Sometimes it refines. You think endurance means resisting all influence. But endurance can also mean integrating influence without collapsing. Roman marine concrete did not shut out the sea. It absorbed it, reacted with it, transformed because of it. This reframes durability in a way that reaches beyond material science. In modern culture, we often equate optimization with immediate performance, fast results, rapid scaling. Instant validation, we design for short feedback cycles. Ancient concrete reminds us that some systems mature across centuries. It also humbles our sense of technological superiority. We possess advanced computational models, high-temperature kilns, precise chemical analysis. Yet in some environments, a mixture of lime and volcanic ash outperforms modern concrete across millennia. The lesson is not that the past was smarter. The lesson is that progress is not linear. Sometimes older systems embed forms of resilience that modern priorities overlook. Sometimes imperfection, like lime clasts scattered through a matrix, creates future adaptability. Sometimes porosity is not a flaw, but an invitation for growth. When you look at a Roman harbor wall now, you are not just seeing preserved history. You are seeing a material that is still participating in its environment, still adjusting, still becoming. That idea is unsettling in a quiet way. We imagine the world is divided into living things that change and inanimate objects that remain fixed. But even stone is negotiating with time. The boundary between static and dynamic is thinner than it appears. So perhaps the most uncomfortable truth is not that concrete hardens for 2,000 years. It is that solidity itself is less absolute than we assume. What feels finished may still be unfolding. What seems inert may still be reacting. And what endures longest may not be what resists change, but what is designed to evolve within it.